And whoa. Imagine looking into a mirror and seeing the back of your head. That's what I do. All right. I'm hoping you can hear my voice. The sound bar says you can. We'll get started in just a moment. We're gonna get started in just a moment. Figuring out, it's the first time I've used this room in like a year, so but everything seems to be working okay. Nothing's changed. Just seems. I was in the other room from my other class, so it seems like this is working. Hopefully the volume is okay. This room is a little bit smaller than the other. Whoa, whoa, whoa. So hopefully the audio, it's kind of strange. I have to keep in mind that I need to talk to the screen because that's where the microphone is. So in the other class, I'll like turn around to address the camera and then I go muffled and you can't quite hear what I'm saying. So it's kind of weird. So I'm probably gonna have my back to y'all a lot because that's how we get the good audio. So I think we're being recorded. So that's good. That means that you'll have a log of this. So if I go a little too fast, and I usually go a little too fast because I'm trying to cram in, gosh, almost. Well, 2 weeks worth of material in one day. So that's quite a bit. But the good thing is it's recorded and so you'll be able to go back and there's a few good things that I can address. If you're joining us online, thank you for joining class live. If you could say something like hi, hey, hello in the chat, just so it logs that you're here. Yeah, so as long as you're signed in, you just say something in the chat, it'll log that you're participating. And I see your names here, so thank you for participating there. That's awesome. Yeah, so just say hi. And then we will take a break in the middle. And when we do that, when we come back, I'll have you say another thing just to log that you came back. So technical difficulties are inevitable. So if something weird is going on, don't hesitate to say something. I think you should be able to see the course website now. Okay. And the first thing I want to bring up is how to get everything. So at home, I use a MacBook, which is in the end is kind of good because I get kind of the experience of students and I get the experience of teachers because at school we only use Windows computers. So I kind of have feelings, I can kind of touch base with both of those, but I can say on the Mac side, I cannot open the materials using Safari. I've reached out, this is not just our class, this is other classes. I've reached out and they said, It's either something in Safari with their privacy settings, and I've adjusted as much as I could. I couldn't get it. So I downloaded Chrome, and I'm using Chrome on my MacBook, and that's the only way I've been able to get it. And then I'm using Chrome right now for our, you know, so Chrome seems to work, okay? I will also say, you know, at home, I use an iPad. I like, you know, especially with mathy type things, it's easier just to write something down and send it to someone. And I have yet to be able to open our course materials through my iPad. So I can open the book, but I can't open it. So I just wanted to let you know that if you're having that problem, it's not just you. But Chrome seems to work, Firefox seems to work. That's all I've got to work, okay? I've contacted our technical team and they said they don't know. So that's that. But how do you get to those materials is you want to go to the Ivy Plus bookshelf in our course website. And that is located here at the Ivy Plus bookshelf. So we want to open that. So that's what I'm gonna do. Of course, it's gonna look different on my computer than it looks on yours because I'm an instructor, you're a student, so it's gonna look a little different. I'll at least show you. You wanna click that Ivy Plus bookshelf and then launch courseware. And that's where they're gonna kind of diverge a little bit. Because you won't have instructor tools, you'll have student tools. So that should be where you wanna go, and you just wanna go to all assignments. Okay? That's what you want to do. Once you do that, that's where all of the course will lie. So the course is linked up with our Canvas. We do have additional material in our course website, the Ivy Learn, but all of the assignments and the quizzes and then eventually the exam is through that. So that's the best way to get it. That's where your textbook is. You don't have to pay for anything. It's all included in our Ivy Tech tuition. So don't pay for anything extra. It's all included. So be sure. But a student in my finite class was saying you did have to register with your Pearson, or it asks you to sign up something, an account or something. I can't replicate it as an instructor. So yeah, just if it seems obvious, just sign up. You know, I hate all the technical issues and, you know, math is confusing enough for everyone. So it's too bad that we have all this, but at least we can offer it to the most amount of people in the most convenient way. Okay, so let's go back to bookshelf, and if you go to modules, you'll see that there's a lot of extra material. So if you go to this modules right here, you're going to see that there's a great deal of material. There's some cheat sheets. There's let's go student view. Student view. There should be under module 1. Should have some learning activities that and the like. So you'll have some, there's all kinds of content in here. So there you have some material. I think there's more. Let's say there was some learning activities and that kind of thing. And then there's also in the homework itself, there are videos and help and all of that. What's this? When will the module 1 check-in quiz be for the syllabus available? Thank you for asking that. We don't really need to do the syllabus quiz or anything like that. I just want to focus on, I should say, I inherited the course website. The only thing I'm really worried about, there's going to be 2 homeworks and 2 quizzes that you have to do for this week. It's the only thing I'm worried about, okay? I know other instructors, they have like in-class activities. They have all these extra things. I don't need to do that. I'm not interested. Just want to help you with your homework, get you prepared for those quizzes, and hopefully in turn, that'll prepare you for the midterm and final, which are the things that we're really worried about. There are some good videos here. Patrick JMT right there. It looks like he's actually online right now. That's fabulous. He's how I learned calculus, by the way. So, 10 or 11 years ago when I was doing it, I watched that guy's videos. So I know they work. So check those out. And there's some good videos. So of course you can just go to YouTube and, plug in, difference quotient, and there'll be a million videos of people watching it. Nancy Pie's great, Khan Academy's great. These are all good videos, classics. Okay, so those are all there if you want them. And then of course you have my lecture, which is recorded and will be posted hopefully tonight. So hopefully that's all you need. But we'll have 4 things due each week, unless it's an exam week. So you'll have 2 homeworks because each week is like 2 weeks for us. So you have 2 homeworks and you have 2 quizzes. And the quizzes are timed, but you get more than 1 try. I think you get 3 tries. I meant to check that. You get 3 tries for my other course, we use Pearson. So I think you're going to get 3 for this. So you get more than 1 try for the quiz, but it is timed. And then the midterm will be timed as well, but that'll be 1 try. If I didn't mention it, my name's Ryan, and you can just call me Ryan. And yeah, I'm always so worried about the technology that I forget to even go over like the basic things. But this is calculus class, brief calc. What is brief calc? Brief calc, in my opinion, is kind of like calculus without trigonometry. So we won't have too much, we'll have no trig at all. Sometimes this course is called business calculus. I've heard it called business calculus before. That's a version of this. I think the textbook is technically calculus with applications brief version, something like that. But we just don't have to worry about trigonomic functions. So we'll mostly just worry about algebraic expression. So if you took something like college algebra before, or in high school, if you took something like pre-calculus before the trig portion, or however it was taught in your high school. But yeah, we don't really need things like sine, cosine, tangent. We're not going to focus on those. So that's the deal. What is calculus? So in some sense, what we're going over and for our course is going to be what is kind of an introduction of where algebra was starting to fall apart, was starting to not be sufficient enough to understand. And if you took something like pre-calculus, now where is algebra not sufficient? If the variable is changing, so a variable like x changes. You can put different values in it. That's mostly what we're going to look at today. But what if the variable itself is changing? Or what if something is not just static? What if it's moving? Okay, so if things are moving, that's when we need to decide how we could study that. So that's it. So the first thing we're really going to understand is, like how you would determine the speed of something. So that would be of interest to us, but it could be anything that's changed. So like I said, with business calc, it could be, how the profits are changing. So we can do something abstract, but still in everyday life. We can determine what that means for things to change. Some people say that calculus is the study of infinity, which is true, but a lot of the time we don't have to think of it quite that abstractly, though we will deal with infinity in some way. But there's always that interesting thing that what happens when something goes to 0 or what happens when something goes to infinity, and calculus really looks at that. But I kind of think of brief calc as almost like a super algebra. It's super algebra class, okay? Advanced algebra course, right? So again, most of our course will lie in the Ivy Plus bookshelf. We're using the Pearson MyMathLab materials this semester. So I'm going to go there and I'm just going to get started. So I've experimented a lot with how to teach a course like this because of the online nature. Sometimes people are in class, sometimes they're out of class. They might be looking at a recording. They might be, So how to do it. And what I found is for this type of course, I found that it's just kind of better to lead with example and then go and explain that rather than go heavy into the theory and then try to shove in some examples. I find that my traditional class, when everybody's in class, we can kind of go the other way where we look more at the theory. But so I'm going to probably lead more with example in this course. So when I do this, I'll probably just be looking at select homework problems and really diving into them, trying to explain them, pick them apart, what this means, and the content within that problem. So it might not be the quickest way to solve the problem. That might not be my goal, is to solve the problem as fast as possible, but really just explain what's going on. And the first few sections will just be review. So ideally, you've had some kind of pre-calculus or college algebra or something. So that's what we're going to do. So I'm going to take a look at homework 1, and this is all review. And I'm going to take a look at some problems. I have some problems selected that I wanted to take a look at. Oh, and I should mention, you're allowed to have a graphing calculator, or this is a graphing calculator course. So, so if you have a graphing calculator, great. If you can borrow one from a friend, great. I hate for anyone to buy one because they're so expensive. They're almost the same price as they were when I was in high school. It seems like a Texas Instruments calculator is over $100, which seems kind of exorbitant. When you're doing your homework or quiz, of course, you can just use an online tool. If you want to graph something, you could use something like Desmos. If you want to calculate something, there's some great graphing calculators for phones or tablets that you can get for free or reduced price. But Desmos is a great free tool. For the exam, you probably want to have at least a scientific calculator at bare minimum. And if you can get a hold of a graphic calculator, I think it would help. I have a real life graphing calculator here that I got from the math department, and then I'll have a digital one that I can show during class. But yeah, if you have a graphing calculator, that's great. If you can borrow one from a friend, family, or someone that I think would help you for the next 8 weeks, that would be good. But you'd want at least a scientific calculator. Okay. So I'm going to close the door because we do have some young campers here. So we can at least take a look. On. I won't be able to go with all the problems. I've got some I'm looking at specifically. Interest. Okay. So yeah, I mean, this is review for sure. But what was I gonna say? So yeah, I won't be able to go over all the problems, and This class does have a lot of problems, but a lot of them are really quick if you know what to do. Sometimes you can get stuck though, of course. And I will say for the harder sections, they do get smaller, but we tend to have a lot of homework, but I'm going to show some homework problems in class, so hopefully that will speed things up for you, okay? So let me look at my list, which ones I want to. So for problem 1, we just have y equals -3/2 x plus 1. This is referring to just a straight line. Y equals mx plus b. Everyone remembers this from high school. Y equals mx plus b, where m is the slope. And slope is the rate of change. Rate of change is something we're going to dive in heavily in this class. What would be the rate of change if it wasn't a straight line? That is to say, like, what would be the slope of something that has curve to it? We can determine what that means very shortly. But m is the slope, the rate of change. Why would we use the letter m for something that stands for slope? Well, that's because a French guy developed this, and it's the French word. It's like mountainous. It just means to climb. So it's just talking about how does this line climb? That's what's going on. There is a slope formula. You can take the difference of the y's over the difference of the x's. So those are the points, the ordered pairs. We can also say that this is rise over run. That's another way to describe this. Here we have -3/2 x plus 1, where 1 is the y-intercept. That's b equals 1, or you can think of it as the ordered pair 0, 1. The y-intercept is the base. So if we're thinking this in terms of mountains or climbing mountains, this is our base, where it starts. And here you can see this is where we're thinking of it, the base, the y-intercept, or intercepts the y-axis. And how is it changing? Well, it's 3 over 2. So you could think of it, it's going down 3 over 2. You can think of it that way. Or you could think of it as going right 3 down 2, but that's where the negative sign comes in, and you have to determine how you're thinking about it. But that's at least a good review of what lines are. Y equals mx plus b, you can guarantee we're going to talk about it all summer long. Lines are very easy to talk about, and so even when we're talking about things that aren't line, we'll go, well, here it's a line. If we zoom in close enough, it's a line. So let's think about it as a line from here to here. So we'll talk about lines all the time, and that is the y-intercept form, okay? Hopefully that's just review. Do the first few problems. Here we have the general form of a line, something like ax plus by equals c. This is the general form of a line. And we're supposed to graph the line. Well, it doesn't say this. I wish it did. We should find the x and y intercepts. X and y intercepts. So, well, we can see, I already graphed it, so you can see what they are here. But if you were given something, a line in the general form, how would you find the x and y intercepts? So the x-intercept would imply that y equals 0. That's when a line would cross the x-axis. If y equals 0, we would have -4x equals 20. We would divide both sides by -4, and we would get x equals -5. Easy enough. So you can see, okay, well, that's at -5. We could also write that as an ordered pair. There you go. What about the y-intercept? Well, the y-intercept implies that x equals 0. If x equals 0, then our equation is 5y equals 20. We would divide both sides by 5, and we would just get 4. So y equals 4. Or you could think of b equals 4. Or you could think of it as 0, 4. Lots of different ways to think about it. They would all be the same. And so if I was graphing this, that's how I would graph it. I have 2 points, and that's the minimum you need to graph a line. Just need 2 points and connect them, and that's it. Okay, so that's getting us going on lines. We've seen the slope form, and we've seen the general form. So easy stuff. Okay. Since we're looking at the homework, I should mention. If you get stuck, okay, let's say you're looking at this word problem, it's not making any sense. Well, hopefully after I explain it, it makes a lot of sense. But with this, we do have some pretty good help. You can view more help. You have the textbook and Ask My Instructor. Maybe not so good for this one. But you have View an Example. You guys have probably seen this before. But they have pretty much a write-out of exactly how to do it. And I'll say, so you know, I probably won't do it how they do it, but that's great for you because then you at least see 2 ways to talk, right? So I probably won't always explain it the same way as they do in the book, but maybe that's good. That way you'll see 2 ways. I feel, to stick up for myself a little bit, I feel like I'm a bit more to the point than those explanations could be. But nevertheless, you'll have that for every problem, so that's good. It says the model H described by H equals 2.75x plus 71.48 can be used to predict the height in centimeters of a woman whose humerus, the bone from the elbow to the shoulder, is X centimeters long. Predict the height of a woman whose humerus is 46 centimeters long. Okay, so what do? Got H equals 2.75x plus 71.48. It said this function is predicting, and we wanted 46. So I think we want to predict with just x equals 46. So we just want to plug that in. So h equals 2.75 times 46 plus 71.48. So you want to get a calculator. Remember PEMDAS. Work on that. So let's see if my calculator is working. Okay. Hopefully it is. First test. Okay. So I want 0.75. 46 plus 71.48. And I'm getting that's 197.98. Now, of course, we could calculate that by hand, but we don't have to. We don't have to. If we don't want to, we can just quickly do this and move on to the next problem. But that's how I was able to calculate. Okay. So that's problem 3. Let's see. I wanted to look at 4. I also want to look at 5. Yeah, here we go. Suppose that $60,000 is invested at 7% interest. Find the amount of money in the account after 6 years if the interest is compounded annually. So this is one of those moments where I'm going to dive just a pinch into theory, and then I'll solve the problem for us. But I just want to say, recall the formula. So remember that there's this compound interest formula. We have rate over the number of times it's compounded, and the number of times it's compounded times the time. Okay? So we want to remember that formula. If you don't remember it, now you got it. There it is. What does P stand for? That's the principal. That's the amount we put into the account. Okay? The R is the rate at which the bank is giving us. Maybe we're doing a car loan or something like that. So the bank gives us a rate, or the dealership gives us a rate. So that's the rate. You want to remember to put that as a decimal though. And then n is the number of times it compounds. Okay, so and then notice that that's the same n. Okay, that's the same n. Those are the two same numbers right there. So I say all that, but in this problem it says compounded annually. So if it's compounded annually, that's just once a year. So the n just goes to 1. All right. But I wanted to bring up at least where this is coming from. So we have n equals 1 here. All right. So the principal here is 60,000. 1 plus 0.07. I guess I didn't need to write it that way because I only have it over 1. And then how long are we doing this? 6 years. So because this is annual, those n's are just turning into 1. And so it simplifies our formula quite a bit. All right, so I should be able to plug this in my calculator, come up with that number. Plus 0.07 to the 6th. And we're going to have to round to the nearest cent, of course. It looks like we've done it. So we find if we round to the nearest cent, it'd be 82 cents. So $90,043.82 there. You see that is the correct answer. Okay, but that's where that's coming from. Hopefully you remember. And then a little bit later in the course, we're going to learn, well, later today we'll talk about what if n isn't 1. We'll talk about that. But just like in calculus, what if n, so what if it compounded quarterly? Well, then n would be 4. What if it compounded monthly? N would be 12. What if it compounded daily? Well, if it compounded daily, that'd be 365. And what if it continuously compounded? So what if n went to infinity? What would happen then? Well, that's something we're going to talk about later, because that's of something of great interest in calculus is what if this went to 0 and what if this went to infinity? That's always what we're thinking about. Right? That's something that mathematicians are always thinking about. All right, so that's 4. I wanted to talk about 5. Okay, so there's some good stuff in 5. Here we have function is given g of x, x squared minus 1, and it wants us to evaluate at -2, 0, 2, a plus h, and then this wild thing, which is called the difference quotient. This problem doesn't call it that, but we're going to look at the difference quotient, and we're going to need to do that. Now, I know when I teach college algebra, my students really struggle with that. So just in case you struggle with it, we need to work on it, okay? And maybe we need to look at this notation here. So when you see something like this, g of -2, that means we're plugging in -2 for x. So g of -2 is -2 squared minus 1. All right, well, I claim that's 4 minus 1, which is 3. We see that notation there. And then what if you plugged in 0? G of 0 would be 0 squared minus 1. And that's, of course, -1, because 0 times 0 is 0, and 0 minus 1 is 1. All right, what about g of 2? Well, what's that? So that's 4 minus 1. That's also 3. It's interesting. If we plugged in the negative number, we did the same thing as if we plugged in the positive number. It's kind of interesting. All right, what is this g of a plus h? This is where I've seen some of my students get lost. So we want to plug in a plus h where we've been plugging in numbers. So how do you do that? A plus h squared minus 1. Well, it turns out the computer is happy with that. That's good enough for the computer, and so I suppose it's good enough for me. Right? But when we do this next part, got to be a little bit more rigorous. Okay. Does it make sense what I mean by plugging in A plus H? Is everybody okay with that? Give me a yeah or something. Does that make sense? I plugged in the letters A plus H where I was evaluating those numbers. Does that make sense? Okay, thanks. Just want to double check. That's sometimes where I lose folks. All right. Now, what about this g of x plus h minus g of x over h? This is where it gets a little wild. So what is g of x plus h? Well, that's going to be very similar to what we just did with the a plus h. So that's going to be x plus h squared minus 1, of course. So that's the first part. I'm going to choose to expand that because I really want to look at this and see how this is working. So that would be x plus h times x plus h minus 1. That's what squared means. It means times itself that many times, 2 times. So let's figure out what this is. That's x squared plus hx plus hx plus h squared minus 1. I'm going to combine like terms if possible, and it is possible. So that's x squared plus 2hx minus 1. Oh, and then there's forgot a term. Plus h squared minus 1. There we go. That's better. So that's that first part. Now let's look, what are we trying to do? We're trying to take g of x plus h minus g of x. That's what we're trying to do. But I found g of x plus h. Now I want to subtract g of x. All right. I'm going to switch colors so we can at least see what's going on. So g of x, whoops, I don't want vanishing pen. G of x plus h minus g of x equals x squared plus 2hx plus h squared minus 1 minus x squared minus 1. And if we're ready, we can do this over h. That won't really change much. All right, let's cross off what we can, leave what we can't. So I do see that we have an x squared minus an x squared. So that looks like that goes away. We have a negative 1 minus minus 1. So that seems to go away. Okay. So what are we left with? We're left with 2hx plus h squared over h. That's what we have left. Okay. If you can, you always want to get rid of that h in the bottom. And I'll tell you more about that next time. But you always want to get rid of that h in the bottom. And I guess I'll tell you why. Because next week, that h is going to go to 0, and we can't divide by 0. So that's what we're practicing. We always want to get rid of an h if we can. So I'm going to factor out an h out of the numerator there. And that would give me 2x plus h, so that was squared, over h. And now we have h over h, and that cancels. And so that leaves me with 2x plus h. That's what I think it is. All right, that's a lot, but I liked it. Is there any questions? Would anyone like to see me do it again? Because this turns out to be one of our more important calculations this week. Okay. It's a lot of steps, but I feel like each step is fairly easy. So it does take a bit of bookkeeping just to watch what you're doing. Each step I think is okay, but you just got to know what you're doing. Is there any questions? Does anyone want me to do it again? Let me save a picture of it. Okay. Next one I want to talk about is problem 9. Well, guess what it is? It's more of that. We're going to find the difference quotient of this function. Okay. So remember, we want to get rid of that h in the bottom, if possible. So here we want to find f of x plus h minus f of x over h. Okay. So what do we got? We got negative 4x plus h squared minus x plus h minus 2. So far, so good, I think. And then we want to subtract f of x and then that's over h. Now I need to expand that x plus h squared. That's what we did in the previous problem. We expanded that. And so I want to do that again. And I am going to use a shortcut. So I'll let you know about that shortcut. Maybe you saw this in an algebra course. If you haven't in a while, here you go. That's a squared plus 2ab plus b squared. We actually showed that in the previous problem. But that can be really helpful, especially when you're dealing with something like this. So I'm going to use that idea in this problem. So that would be negative 4 times x squared plus 2hx plus h squared minus x minus h minus 2 plus 4x squared plus x plus 2 all over h. Okay. And there's going to be some consequences. There's going to be terms that are going to drop out because of what we just did. So we have negative 4x squared minus 8hx minus 4h squared minus x minus h minus 2 plus 4x squared plus x plus 2 all over h. Let's see what cancels. There's always something that's going to cancel. Looks like the 4x squareds cancel. What else cancels? The lone x's cancel. The 2's cancel. Anything else? I think that's it. Okay, so let's put it together now. I got negative 8hx minus 4h squared minus h over h. If we can, we want to factor out an h of the top because we want to get rid of that one in the bottom. So everything has an h in it. So h negative 8x minus 4h minus 1 over h. And that reduces. So there you have the solution. Negative 8x minus 4h minus 1 in some order or fashion. See that is the solution. Okay. So that is the difference quotient. And this is going to be a way for us to define what a rate of change is or what the slope at a particular point is for any given function. Okay, so that's fantastic. But I know that's a lot of algebra. It's all, I think relatively, each step is fairly simple, but there's a lot of steps to it. Are there any questions, comments, or concerns about that problem? This is one of our more important calculations, not necessarily this function, but we do really need to understand this calculation. Any steps you might have questions on? Let me make sure I got a picture. No? So that was number 9. I want to go and talk about number 11. Here in number 11, we have that interest again. See, interest. Okay. So the amount of money A of T in a savings account pays 4% interest compounded quarterly for T years with initial investment of P dollars is given by A of T equals P times 1 plus 0.04 over 4 to the 4T. If $4,000 is invested at 4% compounded quarterly, how much will the investment be worth in 9 years? Okay. So we know P is 4,000. We know the rate equals 4%, and we know it's compounded quarterly, and we know the time is 9. So that should be good. Okay, so we just need to recall what that formula is. It pretty much tells us what to do. Like the problem itself gives us the formula, so that's kind of nice. We just have to fill in a few points. So 4,000. 1 plus 0.04. Note that they're taking that rate, making sure it's a decimal. The divided by 4 is because this is quarterly. And then 4, that's the same 4. And then that would be times 9 because they're saying this is over 9 years. So I'm going to get my calculator out and try to calculate that for myself. Okay. 1 plus divided by Uga. Have it. Then we should probably round to the nearest cent, which looks like it would be 8 cents. Okay. So far, so good. That makes sense with how I'm doing that. So yeah, I mean that you probably want at least a scientific calculator if you're going to have to do something with exponents. I mean, you wouldn't really want to have to multiply that thing out against itself 36 times. That would be pretty difficult to do. You could do it, but it would take you a while, and you couldn't make a single mistake during that calculation. Okay. So that's 11. All right, the next few problems I wanted to talk about, there's a chunk starting at 17. And that's a refresher on domain. Domain is really, really important to us in calculus and analysis. So what is the domain of this function? Well, when I think of domain, when I'm trying to find the domain of a function, I try to remember where does the domain break? It's easier to figure out what's not in the domain than what is in the domain, because generally there's infinite numbers in the domain. So the two cases we really want to look out for is case 1, are you dividing by 0? Okay, 1 over x, you can't divide by 0. So if you have an x in the denominator, you have to be careful that you're not dividing by 0. The other case is the square root of x. And if we're taking the square root of x, or maybe x is some expression, we just want to take only the real values for this. So we're just going to look at numbers where x is greater than or equal to 0. And here, x cannot equal 0. Those are the two cases. When I think domain, I'm just looking at those two. If it's either of those cases, or maybe it's both of those cases, that's where I'm concerned about. That's what is not in the domain. Okay, we can't divide by 0, and really we're only interested in real values. So we can take the square root of 0, but we just want to take the square root of positive numbers. Okay, so no negative numbers. With this problem, there's no restrictions at all. It's just a straight line. All lines have all real numbers. Well, it's pretty close to true. But here, there's no restriction to the domain whatsoever. So this would just be all real numbers, okay? In a fancy way of writing, it would just be x is an element of the real numbers, or we could just write the interval notation, which you see here as a choice, from negative infinity to positive infinity, being no missed real number at all, okay? So there's no restrictions. But if you're dividing by an expression, you want to make sure that you're not dividing by 0. And if you're taking the square root of an expression, you want to make sure that that is 0 or above. Okay. Now the next problem, I think there is a restriction. Yeah, here we go. So here we see, okay, in this one we have the square root of an expression, and we're only interested in real values. So I want to make sure that 2 plus 7x is greater than or equal to 0. And I want all of those numbers, which makes that true. Okay, so we have to set up an inequality. We'll still have an infinite amount of numbers. And if we subtract 2 and subtract 2, then we'd have 7x is greater than or equal to -2. And then I could divide by 7, divide by 7. And that would be x is greater than or equal to -2, 7. So you can see where that solution is coming from. I will include the number -2 over 7 because of this equal sign. So you see that equal sign right there. I am going to include that number, but I want all the numbers above that as well. So -2 over 7 to infinity, that's where this bracket is coming in. Brackets come in when you are including the number. So if you have a bracket, you're including those numbers. If you have parentheses, you're excluding those numbers. So before we saw that we excluded the number infinity because you'll never reach it, and you'll never reach negative infinity, but everything in between those we want. So that's the idea. Okay, so with parentheses, we're excluding numbers. With brackets, we're including the numbers. That's the idea. And then with domain, we just want real values, and we can't divide by 0. And I think I want to talk about 19. Yeah, I do. So we want to find the domain here. Let's do it. Here it looks like we might divide by 0, and I don't want to. I have an expression in the denominator, so I want to make sure that x squared minus 25 does not equal 0. I want to make sure that that's true. Okay, so what can I do to make sure that doesn't happen? I need to make sure that x squared does not equal 25. And what values would cause it to do that? If I take the square root of both sides, I would get x does not equal plus or minus 5. That would cause this to go to 0, and I can't divide by 0. So you can see in set builder notation that x cannot equal 5 nor negative 5, because that negative sign would become positive if we stuck it in there. So we don't want to divide by 0. So we're excluding it. Those are not in the domain Again, domain is the input values. Maybe I should have said that before. Domain is the input values of a function. The x values. So what x are allowed? Well, I mean, there's still infinite amount of numbers, right? We're just excluding 2 of them. So from negative infinity to -5, from -5 to 5, and then from 5 to infinity would be an interval notation, which the question did not ask me to do. That's how you could write it. And I think in a future problem, I should explain the union, which is just a U. That's how you would add those sets, but we'll just go over that one. Here it was just a multiple choice question. So domain is all of the numbers that are the input, and generally it's an infinite amount of numbers, so you just need to figure out what numbers are excluded. And here there was only 2 numbers, -5 and +5. Okay. All right, let me take a picture of that. And about 5 till. And let's see, what was the next one I wanted to? 18. Let's take a look at 29. I remember if this was a word problem, what it was that, yeah, it was word. I couldn't remember what it was I wanted to talk about. Okay. So this is where the business is kind of coming into play. We're going to start building these equations, profit, cost, revenue. Later on, we'll start taking derivatives of these, and that kind of expanding on that. But today, we're just going to kind of build them. So we have a corporation that's planning to produce a new graphing calculator. For the first year, the fixed cost for setting up the new production line is $1,005,000, and the variable cost for each calculator is $9. The sales department projects that 125,000 calculators will be sold during the first year at a price of $76 each. Complete parts A through E below. The first part is we want to come up with a cost equation. And I will say I get twisted up with a plus or a minus sign with this. I have to keep it in order. Because I always think of cost as a negative sign, but you have to kind of watch out here. So what is producing each calculator costing the company? Well, they have a new production line. So that is a fixed cost right there. And then each calculator that's produced, I guess this would be for materials, is costing them $9 per calculator. So it is just a straight line with a slope of 9 and a fixed cost of $1,005,000. Okay, so it is just a line. So C, meaning cost of X, is 9X plus 100,500. Okay, and I'm just pulling that from the story problem. So the cost of the calculator for the company is $9 each, and then there's this overall cost. Okay, so that's where that's coming from. Okay. Now, they want you to graph it. That's fairly easy to graph a straight line. You have the y-intercept right there. You have the slope right there. So you just need to pick which one's right. There's not too much mystery there. The revenue, this is the money coming in per calculator. And they told us for the revenue that each calculator will be sold at $76. Okay. Well, if each one sold, we're going to have revenue equation is $76. There we go. So each one sold would be 76 times X, however many we sell. Okay. So fairly easy to understand. Going down, there's some more parts here. So they want you to graph your revenue equation, but that's fairly easy. It's going to go through 0, 0 because it's a y equals mx equation. So it goes through 0, 0. It's positive. So you can see how that's going to go. So, see our revenue equation is right there. And it just has a slope of 76. It's not too difficult to see, but it is positive, of course. We are making money off this. But one thing that I really need to stress, and this is just part of our course, you might have seen it in your other courses, is the profit equation. And the profit equation is built by taking the revenue minus the cost. We need to make sure that we can do that. And in this problem, our revenue was 76x. And our cost was 9x. We need to subtract that. So what's going to happen is we're going to combine like terms, and that fixed cost will become negative, which makes sense because this is costing us money. So we have 6 minus 9. So that'd be 67. So we see our profit equation is 67x minus 1, 0, 0, 5, 0, 0, 0. That's our profit equation. And then you can graph that, but it has a negative y-intercept. This is the B, this is the M. So you'll see that. But from there, you would just graph it and choose which is correct. We can see what that graph would look like right there. That makes sense. So that looks good. Okay. But the profit equation is important to us. We're going to look at a lot of business applications in the course. So we need to remember how to do that. It's fairly easy. And the nice thing is all three of those were straight lines. So not too bad. Not too bad. When they're not a straight line, it'll be more confusing, of course. You know, if we have something that's quadratic, it can be a bit more difficult, but the idea would be the exact same. So keep an eye on those cost, revenue, and profit equations. Did you need to go back? Okay. And if you have any questions online, don't hesitate to put it in the chat, at the chat board. All right, next one I wanted to pull up was the next question. All right, we're gonna mow some lawns. Jimmy's gonna mow some lawns. The initial cost of the electric mower was $250. Maintenance is $4 per lawn. And we wanna come up with a cost equation, revenue equation, and then charge per line. Okay, so let's see what happens. Well, cost. Okay, so Jimmy's looking at $4 per line, and then there was the initial buy-in at 250. So our cost equation is a variable of 4 plus 250. There's our cost equation. We're charging, where does it say it? Jimmy determines that the profit is 9x minus 250. So what must have been the revenue? So they're kind of asking this a little bit backwards, but we can just look at the 9x and the 4x. What must they be charging? If we subtracted those, what must it have been? Well, it must have been 13 for this one. Okay, of course, that's not too bad. If it equals 9x, then this must have been 13x minus 4x, because we get the revenue. So that it's kind of asking the same question a little backwards, but it's okay. But you really have to know where it comes from to find that. All right, And then how much does Jimmy charge per line? Well, we just found, okay, so there must be a revenue of $13 for this. So there's 13. How many lawns must be before we start making a profit? This is asking a really important question, but it didn't use the word that I wanted. We need to see where we break even. That's really important to us. So we need to see where is the break even point? You can take the profit equation and set it equal to 0. So P of X equals 0 is 9X minus 250 equals 0. That is to say, we just need to figure out what 250 divided by 9 is. And I found it was 27 and change when I did it. Show you. And I just rounded to the nearest lawn. Let's see. 250 over 9. Let's see, we get 27.7 repeating. And so to the nearest lawn, it's 28 lawns. But that would be the break-even point. After that, after the 28th lawn, that's where the profit begins. Okay. Any questions about that one? The next one I wanted to look at was 31. Yeah. 31. The revenue R of X, cost C of X, profit P of X for a product are graphed in the figure to the right, where X is the quantity produced and sold. Determine the break-even quantity, find the equations of the 3 functions, and determine the fixed cost produced of each item, selling price of each item, and the net profit of each item. Okay, so the first part is we just are asked what is the break even, and they already graphed it for us. So I'm going to pull that graph up, and maybe we can just see where it's coming in. If my computer will pull this up. Okay, let's see if we can figure out what's going on here. I see we have revenue at top, cost in the middle, profit at the bottom. Where is that break even point? Well, it looks like where revenue and cost cross would be where it breaks even. And so that looks like that's happening at 10. That's where revenue and cost are crossing. So I think it's at X equals 10. Okay. That's where I believe that would be crossing. So let me clear that. Try to show that. So the break-even quantity is 10 items. Okay. Next part is, what is the profit equation? What is the revenue equation? What is the cost equation? Let me fold that graph up again and see if I can describe it. So these are straight lines. So y equals mx plus b, right? So we can just use our y equals mx plus b techniques and just go right from where we need to go. All right, look, what are we asked to do first? Profit. So let's do profit. So I'm looking at this, okay, profit equation. I see that the profit equation has a y-intercept of -30. So profit equation, I have b equals -30. Already got that ready to go. Now, I need to figure out that slope. How do I figure out slope? Well, I think we could just figure out, if we figure out 2 points, we're good. We already have 1 point down. Let's find the other. So it looks like we have the point 20, 30 there. So we have 20, 30 as a point. And another point we have is 0, -30. That should do. Okay, so we can find the slope. Once we find the slope, then we have the equation of the line. So let's do that. Okay, so m equals -30 minus 30. over 0 minus 20, negative 60 over negative 20. Cancel zeros, make it positive. Looks like it's 3. So it looks like my slope is a 3. And so I think my equation for P of x equals 3x minus 30. Right? You can see it's a little shaded, but hopefully you can still see it on Zoom. Okay. Any questions, comments, or concerns about how I found that profit equation? I would do the very same for revenue and cost. As a matter of fact, that's what I did. With your permission, I'm going to move on to another example. Is there anyone that has any questions about how to find it or how I might move on? I have one more to do before the break. Okay, so it's just a straight line. You already have the y-intercept. That's easy enough. And from there, it should be easy stuff. Do that. And the next question I wanted to go over was 46. I don't remember what I wanted to say about it. Equilibrium point, that's what I wanted to talk about. Yeah. 46. I had a note about this. Let's see. All right, find the equilibrium point for a pair of demand and supply function. Here, Q represents the number of units produced in thousands. X is the price in dollars. The demand is Q equals 5,400 minus X. The supply is Q equals 400 plus 50X. I think of this still as break even. If we think of Jimmy and his lawns, we're still thinking of break even. Think of cost and revenue. When they cross, that's when we break even. When demand and supply cross, that's our equilibrium point. So let's set these equal to each other. If we set these equal to each other, Q equals Q, that would find us our equilibrium point. So let's do it. Again, 5,400 minus 50x equals 400 plus 50x. Okay, we should move things around so we have what we need. Looks like we could add 50x to both sides, and we could subtract 400 to both sides. We would have 5,000 equals 100x. And if I divide both sides by 100, we would just have x equals 50. If x equals 50, what is the point? What is the equilibrium point? I'm going to plug this in to my demand and see what happens. So I solved where they cross. Now, what happens if I plug that in? I get Q equals 5,400 minus 50 times 50. 5 times 5 is 25. And so we can see where I'm getting 29 there. Calculate it back on. So we have 5,400 minus 50 times 50. And there we go with 2,900. Okay. So that's the idea. Equilibrium is where those are equal to each other. Okay. Easy enough, I think. Nice thing is they're all lines, they're all straight lines. So that makes it easy enough. And then I found what the x would have to be, and I plugged it into my demand equation, and there you have it. Okay, so that's the point. And it wanted it as an ordered pair, so I typed it in as an x and a y. There are a lot of homework problems for this course. It's, believe it or not, it's not my fault. it seems that when I compare it to the other class in teaching finance, you guys have more problems, but each problem is a little bit quicker. But that can be annoying if one of them gets sticky. They have about 20 problems per homework, and this one we have at least 46. So there is a lot of problems. So that's just par for the course, I guess. So if you get stuck on one of the other ones, let me know. Try to respond as quickly as possible, but that is an introduction to the first homework that will be due next week. So yeah, I think now is a good time to take a break. Since we've looked at the first homework, I'm gonna take a 10-minute break and then we'll come back and we'll look at part B of the homework, where we'll actually start talking about some calculus ideas. Okay. All right, I'll take a 10-minute and then come back. Look at part B.
So you can redo questions?
Oh yeah, you can do them, please.
Oh, okay.
Yeah. Yeah, that's one of the big things. Having online homework. Hello, internet world. So if you're back from the break, could you write your favorite kids movie or favorite movie as a kid that you enjoyed? That would be great. So if you could write that in the chat, your favorite kids movie or your favorite movie as a kid. See who's back. Everybody's doing good. Yeah, so hopefully, I never know how to teach these courses because we change format every year. So it's kind of strange. So this is quite a bit different than how I learned calculus, but hopefully you will be able to complete it. I mean, this is just an intro, so should be fine. But I find that with my online classes, people prefer a little bit more example oriented than in-depth theory, but I'll just go into the theory when we need to and then kind of do it that way. Also, this is a brief calc and not the full calculus where we have to do proofs and that kind of thing. So it's a little bit more application oriented as the textbook tells us. So yeah, if you're back from the break, if you can write your favorite kids movie or favorite movie as a kid. I see some non-kids movies here, but I see some kid movies. Cars always seems to be a popular one. Is that Cars 1, 2, 3, or Cars on the Road? There's so many. Dark Knight, that's pretty grim for a kids movie. Tomb Raider, sure. Home Alone, classic. Yeah. Okay. Finding Dory, yes. Very good. Yeah. Okay. So the next thing we're going to do is we're actually going to introduce a calculus idea, which is the limit of a function. So as x approaches a number, what's happening to the function? And that is a critical, super important first key point to calculus is the concept of a limit, and that's what we're going to tackle next. Luckily, for the most part, these problems are very simple, and we don't have to prove anything. We don't need to use any epsilon delta proofs for our course. We're really focused on application, so I think that will be just fine. What becomes confusing is that we can take the limit of a function even if a particular value is outside of the domain. So before the break, we talked about domain, what happens, like for instance, dividing by 0, what happens when x approaches 0? Well, we're going to talk about that. So that's where it gets interesting. Like I say, calculus is something that's really interested in what happens if it's 0, what happens if it goes to infinity or negative. Those are things we're really interested in. Okay. I guess another thing I should have mentioned before, and I didn't, was I don't really have office hours anymore. So there's no real office hours for this course because I guess in some sense it's always out office hours. So you can always just email me and ask me a question. And in fact, in the homework, love that homework. So even in this first problem, you can get more help. You can ask my instructor, and this is supposed to email me a question. That's my email address right there, brianpennell@ivytech.com. And so that's the best way to get hold of me. You can also just email me and ask me a question. So I don't really have traditional office hours anymore because no one really comes to them. And I'm also only a part-time instructor. I'm not a full-time staff. So I don't have an office or anything. But that's okay. You can just email me and I'm pretty quick to respond, especially if it's a very specific question. I can answer fairly. Yeah. I should mention this again, but I did just check and it looks like the quizzes. So you have 2 quizzes due each week, 2 homeworks, 2 quizzes. The quizzes, it looks like you have 2 attempts. You have 2 attempts on the quizzes. So at least it's not just one, right? So you should be able to take the quiz, see how you did, and then take it again, and it'll save the best score. Okay. All right. So should help. All right. So we are looking at. Oops. We were looking. Section 1B. This working. Difficulties. There we go. Sorry about that. Okay. Just doing that. Okay. As x approaches 2, the value of 2x plus 6 approaches what? So this is just a baby step into limits. I'm just gonna throw this right in there. So LIM for limit. As x goes to or becomes the number 2, what is the value of 2x plus 6? Well, first question I'm going to ask myself is, what just happens if x equals? What if it just equals 2? So that would be 2 times 2 plus 6, and that's just 10. Okay, so that's not too difficult. All I do is 2 times 2 plus 6. All right, well, not too fascinating. So the answer is just 10. Okay, whoop-de-doo. But the deal with the limit is, the definition of one is it has to exist on both sides, okay? And we're going to see that through the homework. So the limit needs to exist on both the left and the right side. And that doesn't really come up with something like 2x plus 6, just a straight line, but it will come up with other functions. So we're going to introduce things like the limit as x approaches 2 from the left. That would be something like 1.9, 1.99, 1.999. And as it gets closer and closer and closer and closer to 2, what is this going towards? We're going to talk about that. And then we're also going to talk about coming from the right. Put a little plus sign there. So what if we had 2.1? Where is it going? What about 2.01? Where is this going? 2.001, 2.0001, and so on and so on and so on. Where is this function going? Well, it's going to 10. No problem. And if it's the same on both sides, then the limit exists. That's the idea. But this is just a straight line, so of course it exists. And we can just plug in the number and we're done. But that's the idea of this limit. It has to exist on both sides. It doesn't really happen with something so simple as a straight line, but we need to watch out, especially when we're dividing by 0. That's a big deal. Taking the square root of a negative number, something like that. We just gotta be careful. Okay? So it's gotta exist on both sides. And then we'll also see that visually with graphs. Let's take a look at the second question. The notation blank is read the limit as x approaches 2 from the right. This is what I've been rambling about. So the limit as x approaches 2 to the right, from the right, this is that 2 plus symbol, okay? From the right of 2. So you can think of 2.1, 2.01, 2.001, 2.0001, and so on and so on and so on, infinitely getting closer to 2 from the right. Okay, so we're going just a little bit more than 2, but we're getting closer and closer and closer to 2 on the number line. So if we think of this is 0 and this is 2, we're coming from this way. And we're getting closer and closer and closer to 2. And how this function works. So the little plus sign tells us that that's going from the right. And this says as approaching from the right. So we have the limit x approaches 2 from the right. That's the idea. So we're getting closer and closer and closer to 2 from the right. If it's from the left, we'd have a negative sign. We would just be below 2 and we'd be getting closer and closer to 2. Okay, so that's what the plus and minus sign is having to do with the left and right. And when I teach the college algebra course, which is like a pre-calculus course here, we touch on that for like just a couple questions and then we just drop it. So I can imagine if you took that course, you wouldn't remember it. So now we have to kind of remember it, or learn it from the first time, which is most likely the case. Let's keep going. The notation limit as x approaches 4 f of x is read. I basically read it out loud. Just looking at the notation there. It's the limit as x approaches 4 of f of x. That's just in case you're really rusty. That's not f times x, that's f of x, where we're evaluating numbers like we saw g of -2 earlier. This is f of x. Not f times x, but f of x, where f of x is some function. Could be a line, could be, it could be a quadratic or something like that. So that's how we would read it. And let's get 5. Use the graph of f to find the given limit. When necessary, state the limit does not exist. Okay. So I got to look at the graph. Here's my graph. Hopefully the Zoom folks can see this. And I do see that there is a jump in continuity here. That's interesting. And I did mention something about the limit has to be the same on both sides for it to exist. This is where that's going to come up. So we got to be careful. Now we're interested in the number 6. X equals 6 right here. So we're looking at there. Okay. What's going on? If I look at this from the left, going that way, okay, it looks like it's going there. If I'm coming from the right, it's going the same spot. So it looks like it does exist. It does seem like it's going to the same place. Where is that place? Looks like it's the number 8. So it's going to the number 8 here. Okay, so I think the limit equals 8, right? Cool. Now, let's look at, just because we have a spot to actually think about it visually now, let's look at the spot where the limit doesn't exist. How about over here where things are getting a little crazy? If you look right there, what number is that? That's 4, 3. So it looks like when x equals -3, there's a bit of a jump there. There's a bit of a jump. So if you're coming at -3 from this side, it's not the same as if you're coming from -3 from the right side. They're not the same. Not the same. So we gotta watch out for that, okay? I mean, we're not missing any points, but they are not the same. Like, if we come from the right, where's my vanishing pen? If we come from the right, then we're coming over here at 5. Looks like it's getting closer and closer to 5. If we come from the left, it's getting closer and closer to 6. And so those limits from the left and the right are not the same. So we gotta watch out for that. However, that's not what the question asked. That's just what the teacher is rambling on about, because that's the more interesting concept. So for this one, we didn't have any problem. So the limit exists. What's the next one? I can't remember. Use the graph when f is given limit, and this one we did have a problem. So this is the more interesting one. When f of x, when x is approaching -6. So what's going on here? So when we approach from the right, we're getting something like 4. So when I come closer and closer and closer from the right, it looks like I'm getting 4. When I go closer and closer and closer from the left, well, it looks like I'm getting something like 7. Okay. So if I write that idea down, the limit as x approaches -6 from the left, it looks like it's getting closer, and I should be careful with my notation. It looks like it's getting closer and closer to 7, and the limit as x approaches -6 from the right, it looks like it's getting closer and closer to 4, and those are not equal. Those are not equal. So I claim that this limit does not exist at that point. Doesn't exist. So that's what I've chosen. And so I claim that the limit does not exist for that point. Okay. Any questions, comments, or concerns about that? We'll see that more, but this is another really, really important concept. We're kind of warming up to the definition of a limit. Aside from the graph, whether the limit exists, if the limit exists, find its value. The limit of the function as it approaches -1. Well, I found that it did exist, and we want to look at x equals -1 and what's going on. Where's my vanishing pen? So -1, even though it looks like there is a hole right at that point, so it looks like there is a hole right at that point, if I approach it from the left, I'm getting closer and closer to 1. If I approach it from the right, closer and closer and closer to 1. Both of those limits agree. Both of those limits agree. The limit as x approaches -1 for the function f of x seems to be 1, and that was from the left and the right. So those are agreed, even though that point doesn't actually exist. It's not actually on there. There's a little hole there. So the point doesn't actually exist on that function, but we still have a limit. We still know where that limit's going. That's the idea. It's the idea of a limit. More interesting when things don't work than when they do work, but that's the way it goes with math. More interesting to look at when things start breaking. Oops. That was 7. I wanted to show, I think it was 11. Use the graph of G to show the right found limit. If necessary, state the limit does not exist. And I think it was this graph that I found interesting. So the limit of G of X as X approaches 2 from the right. Okay, we're going to 2 to the right. Well, that's not too exciting, I guess. Maybe it was just, I guess it was just a graph I liked. So as we go from the right, looks like we're just going to 0. Nothing too wild there. The more exciting point would be if as X approaches 1, but my question didn't ask that. I would claim that it doesn't exist as X approaches 1, but this question asks as X approaches 2 to the right. So I think the limit as X approaches 2 to the right of G of X as given by the graph would just equal 0. Both sides. Actually, both sides would agree, but we only need one side. Right? Any questions? Chat, don't hesitate to say something. Hopefully it's all working out. So 11. The next one I wanted to look at was 13. Yeah. Use the graph of H shown to the right. Find the limit when necessary. State that it doesn't exist as X approaches -1. Okay, so we're given this function and we're going to -1. Right? X approaches -1. Well, we do have a skip continuity. Not drawing that very well. But from the left and the right, it does seem to be going at that point. There is a skip in continuity right there, but they're still approaching it. So the limit as X approaches -1 from the left of H of X equals 1, and the limit as X approaches -1 from the right, H of X equals 1. So they do agree, even though X equals -1, there's a hole, there's a skip, continuity, and it actually jumps up to 3. But the limit agrees, so we agree with the limit. It has to work for both sides. Kind of funny, I know, but there you go. That's 13. Let me check my notes. I think the next one is 17. Use the graph of F to show on the right to find the given limit when necessary. State that the limit does not exist. In this case, I found it didn't exist, but we'll see why. As X approaches -7. Okay. X approaches -7. We're talking about right here. That's where we're thinking of. What's going on? So as X approaches -7 from the right, and was this F of X? Yeah. it looks like that is going to negative infinity. So that's pretty wild. And the limit as x approaches -7 from the left, should be over here. As it gets closer and closer, it seems to be going up, 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 and that's going to positive infinity. So one way we're going positive infinity, the other way we're going negative infinity. So they certainly do not agree, and they could not be more opposite. So I would suggest this does not exist, that the limit does not exist for the function at that point. Any questions about getting the limit from the left and the right? Does it make sense how I'm doing that? (19) Use the graph of f to show here to find the limit. If necessary, state that the limit does not exist as x goes to infinity. See, as I say, we're always interested in what happens if it goes to 0, what happens if it goes to infinity. Okay, as x approaches infinity, it's having this horizontal asymptote. And it looks to me like it's just getting closer and closer to this value here, which is just 1. So that's kind of interesting. So as it goes off to infinity, it will just get closer and closer and closer to the line y equals 1. So we claim that, yeah, that does exist, and that is going to go to 1. We don't have any conflicting reports here, okay? So that's kind of interesting. If we looked at something like negative x approaches -4 from the left and the right, that would be contradictory, where one is going to positive infinity and the other is going to negative infinity. So I don't think the limit exists there, but I do think it exists as x approaches infinity. Okay, so I think that was the first one where we were plugging in x as infinity. Now we've had the solution be infinity. I think that was the first time we plugged in the number for infinity. And we got to be careful when we talk about that. We're not really plugging in infinity. We're letting x get bigger and bigger. Maybe that's, too much theory, but we're not actually plugging in the number infinity. We're just letting x get huge. Bigger and bigger. And then when it gets really big, we let it get even bigger. Okay. That's the idea. All right, so that was 19. Next one I wanted to look at was 23. Graph the following function. Oh, looks like I need to go up. Graph the following function and then find specific limits. When necessary, state that the limit does not exist. So we are in this version. We're looking at f of x equals 1 over x plus 3. This is where, in that pre-calculus, where you had all those transformations, can be really helpful. This is a vertical transformation. We're lifting the graph of 1 over x up 3, or lifting it up 3, and that's what's going on there. So you might have to review that a little bit, your horizontal and vertical transformations. That just means we're lifting it up or bringing it down if it's vertical, and then shifting it left and right if it's horizontal. Anyway, so we're just taking 1 over x and bringing it up. We can see what that graph would look like here. That's just the graph of 1 over x, but we bring up the values by 3. Okay. If you have no idea where to even start with something like this, you could always plug in some numbers. Right? You could plug in x equals 2 and see what it would equal. X equals 3, see what it equals. See what happens if it's x equals -2, see what happens. Or maybe x equals -3, see what happens. You get kind of an idea of what you're looking at. And of course, if you have a graphing calculator, you can take a look at these things. Let's see if I can pull it up. I showed my screen. Let's see, see that. So if I turn that on, y equals 1 over x. And then let's look at 1 over x plus 3. I think. So it's pretty rudimentary stuff. You can kind of see what's going on. I have 1 over x there, and then I have 1 over x plus 3, and it's just lifting. So that's pretty, reminds me of the first Game Boy graphics. But we could also go to something like Desmos.com, a little bit more modern. Graphic calculator there. F of x equals 1 over x plus some constant. Slider. See how that's working. C starts at 0. You just have 1 over x there, and as C grows, it's just going up. That's kind of interesting. What about the limit as x goes to infinity? All right, as x goes to infinity, few ways to look at. Well, since they have the graph, I'll just talk about the graph first. So as x goes to infinity, you can see, well, what is it approaching? It's approaching 3. It's approaching the line y is 3. So that's easy enough to see when you look at it visually. But how can you understand this without looking at the graph? So more analytically. The limit as x approaches infinity, the function 1 over x plus 3. Think about what happens when you plug larger and larger and larger numbers in for that x. Okay, if you plug in 100, then you have 3.01. If you plug in 1,000 for x, you have 3.001. And that 0 is just going to add on and on and on and on. So let me play with my calculator. Maybe try to show you that. So for instance, if I go back second bit, 1 divided by 100 plus 3, 3.01. 1 divided by 1,000 plus 3. And you can see that 1 is going to shift on and on. 1 divided by 1,000,000 plus 3. And you see it's getting closer and closer and closer to 3. 1 divided by, actually, I'm going to do this live. See what the calculator says when I do this. What if I took 1/10 to the 100 plus 3? I want to see what it's going to say. Yep, it just goes straight to 3. So as it gets closer and closer to infinity, as that x gets larger and larger, this just tends toward 3. Which is another way of saying, and this is important, and I want you to keep this in your notes. I'm going to put blocks here. As x approaches 1 over x, that goes to 0. It's one of our more important concepts today. Okay, so that's what we showed. 1 over x plus 3 just goes to 3 as x gets larger and larger and larger. And that means that as the limit x approaches 1 over x, just goes to 0. That's what we're saying. Okay. That term just is going to be completely negligible. Hopefully that makes sense. And then what was the other part? As x goes to 0, think. Down, maybe. What happens when x goes to 0? So the limit approaches 0 from the left side, 1 over x plus 3. The limit as x approaches 0 from the right, over x plus 3. I claim that they are not the same. I claim that they are not the same. Why is that? Because they're divergent. We can see that from their graph here. So as x approaches 0 from the right, the function is going to infinity. As x approaches 0 from the left, x is going to negative infinity. Analytically, if you, let's say you just use a calculator to try to understand this, if you plug smaller and smaller values in there, you'll see what's going on. So if you plug in, for instance, negative 100 in there, and then negative 1000, then negative, you'll see it's just going to get smaller and smaller and smaller. If you do closer and closer and closer from the right, you'll see it's going to get larger and larger. And since those limits are not the same, this doesn't exist. That's the idea of the limits. They have to agree on both sides, right? So that was a good one. And that was question 23. Okay. What about question 29? Sorry, notes. Use the theorem of limits of rational functions to find the following limit. The limit as x approaches -6 for the function x squared minus 11. Let's see what happens. Is there anything holding us back from just plugging it in? Well, what happens? If we just plug in -6, what happens? That's 36 minus 11, that's 25. No problem. So we can just evaluate it. Easy. We can just evaluate it. There's no problem. We can check if we're scared, if we're nervous that maybe both sides don't work. We could come from the left, make sure that it's working. Come from the right, make sure it's working. And then this, plug it in, just like evaluating the function. X equals -6. So I think the limit is 25. I claim that it is the same on both sides. Another way you could do it is you could graph it. Just make sure you don't have any asymptotes or anything like that. No problem. So that's maybe how you would do let's look at question 1. Now let's look at this one. What's going on with this one? We have the limit as x approaches -4. Okay, so the limit as x approaches -4 for x squared minus 8, 4 minus x. The thing that makes me nervous is that denominator. But I don't know. Let's see. Let's see what happens if we just plug it in. -4 squared minus 8 over 4 minus -4. Okay. Seems like it's okay. As long as that minus sign goes away, I think we're fine. 16 minus 8 over 4 plus 4. That looks like that's just 8. 8 over 8 is just 1. I'm just getting that it evaluates as 1. So it looks like the limit does exist at that point. No problem, I claim that it exists on both sides. It looks like the issue would have been more if x equals 4. As x approaches 4, it looks like we might have a problem. Not as x approaches negative 4. I do not have a problem with this function. Okay. Any questions about that? Comments, concerns, criticisms, like that? Well, next one. I guess I didn't explain what a rational function is, but a rational function is, well, just think ratio. A over B, something like that. Just a ratio. What if you have an expression in the denominator? So that's what we've been thinking about. Next one I wanted to talk about was 33. The initial substitution of x equals a yields the form 0 over 0. Simplify the function algebraically or use the table or graph to determine the limit. If necessary, state that the limit does not exist. So we want to go as x approaches 10. Okay, let's see what happens. Well, so far so good. I've just been plugging in the numbers and I've just been getting out the answer just like evaluating the function, just been giving it out. So I'm going to try that and see what happens. Just going to see what happens. Okay, so I get 10 squared plus 3 times 10 minus 130 over 10 squared minus 100. And I do see an issue. I see a bit of an issue here. That denominator is going to be 100 minus 100. So if I just plug in 10, I'm dividing by 0. And that is an issue. So that's concerning to me. So I don't think that's the path, okay? We need to think of something else. So what did it say? Simplify the function algebraically. Okay. So algebraic, that sounds like I have to remember my algebra. Is there a way of factoring these things? Is there a way to factor x squared plus 3x minus 130? Does anyone remember? Well, if we can think of two terms with 130 that add to positive 3, we would be good to go. Can anyone remember or think of two ways to do that? Two numbers that would multiply to 130 that would add to positive 3. Help me if you can. Two numbers that multiply to 130 add to positive 3. They'd have to be pretty close together. Two numbers. 5 and 8, yeah, 5 and 8 wouldn't add. Or they would add, but they wouldn't multiply. Yeah, so negative 10 and 13 work. Okay, so let's factor them. So we have x minus 10 and x plus 13, and we claim that that's the same. So if you distribute that, you'd see the same. All right, now can we factor out that or can we factor the denominator? X squared minus 100. If you remember your algebra, that's a difference of squares. That's a difference of squares. So that would be x plus plus 10, x minus 10. Okay, so from there, I can say that this is really the same as x minus 10, x plus 13, x plus 10, x minus 10. Okay. So I just factored it. But by doing that, looks like something cancels. X minus 10 is on both top and bottom. So it reduces. So this becomes x plus 13, x plus 10. Now let's try plugging in x equals 10 and see what happens. (23 over 20). There it is. That's what the function is approaching as x approaches 10. There it is. So the limit did exist. Turned out it did exist. Right. And thank you, Vega, for helping me out with that. All right. Any questions, comments, concerns about that one? Does anyone have any questions about that one? Is there any step you want me to do again? I wanted to look at 34, but I don't remember why. Maybe it's just similar to the last one. Okay, let's see what happens. So it says simplify the function algebraically and find the limit as x approaches 3. Okay, so do we have any luck if we just plug in 3? 3 squared plus 4 times 3 minus 21. 3 squared minus 6 times 3 plus 9. That's 9. Where does that go to? Let's see if I can pull up my calculator. Nine plus 12 minus 21. And that's 0. What happens at the bottom there? 9 minus 18 plus 9, 0. And we're running into that 0 over 0 business. Well, that's undefined by definition. So yeah, I guess we're gonna have to do something else. Okay, so if we're gonna do something else, let's do it. Is there a way we could factor that numerator up in some way? X squared plus 4x minus 21. Is there a way to factor this? I need to think of two numbers that multiply to 21 and add to 4. Can anyone think of two numbers that multiply to negative 21 and add to 4? Two numbers that multiply to 20. Yep, thank you, Lucas. We got 3 and 7. So it looks like it's got to be negative 3, just as Lucas said. Okay, so I think we can factor this. So we have x minus 3, x plus 7. Okay, so far so good. Now what about the other one? How can we do this? So we have x squared minus 6x plus 9. Is there two numbers that multiply to 9 and add to negative 6? Can anyone think of those? Two numbers that multiply to 9 and add to negative 6. Yep, thank you, Lucas. Negative 3 and negative 3 multiply to positive 9 and add to negative 6. So it looks like this is x minus 3, x minus 3. And there we go. So we've rearranged this algebraically. So we say, okay, well, this is the same as x minus 3, x plus 7, x minus 3, x minus 3. And just like that previous example, we see that an x minus 3 reduces. Because that reduces, well, we can evaluate. So that's x plus 7, x minus 3. So we say, okay, well, we algebraically reduced it to x plus 7 over x minus 3. That's fine. What happens if you plug in 3? Well, you get 10 on the top, but you get 0 on the bottom. And that's still undefined. Still undefined. And because it's not 0 over 0 anymore, we say this limit doesn't exist. If it was 0 over 0 again, we would keep going. But this is 10 over 0. So this limit does not exist. So the limit does not exist. Okay. Right. Remember our factoring, but any questions about that? Any comments about that? Okay. What are we doing? We got about a half hour. And I have a chunk at the end that I want to talk about. That's the 4. Take a peek, just in case. Oh, what's 39 bro? So before, when I was on my own, I said that this was easy enough. Should be easy enough, but let me look at that again. Use the graph to find the following limits of the function. Limit as x approaches negative infinity. I'm sorry, as x approaches 0 from the left, 0 from the right, 0 so far. So when I was looking at this myself, I thought this should be easy enough. If what we've done so far made sense, this should make sense. So as we go from go to 0 from the left, it looks like it's going to 4. If we're going to 0 from the right, it looks like it's going to 0. So I thought this one probably be easy enough to get a hold of if you were just looking at the instructions. So again, can't go over every problem, but we do have examples here. Those are good. So take a look at those, and then many of them, this one even has a video. So yeah, definitely get the help. And then if you're really stuck, of course, you can just email your instructor. Okay, I have some notes that I wanted to go over a chunk starting at 44. We should take a look at that. All right, find a simplified form of the difference quotient. That's what we've been talking about with that difference quotient, and complete the following table. So f of x equals negative 3x squared. And then we have some x values, some h values. Okay. So the first thing is find the difference quotient. And I remember when I was teaching college algebra that this was difficult for them. So I wanted to go over it many times for you. So what would that difference quotient be? In this case, that would be negative 3x plus h squared minus negative 3x squared over h. Okay. And that's negative 3 squared plus 2hx plus h squared plus 3x squared over h. And I can distribute that negative 3. And I notice that I do have a term cancels, negative 3x squared cancels. So there we have it. And then we have negative 6hx minus 3h squared over h. And I'm going to try that trick we did before where we factor out an h in the numerator. So h would give me negative 6x minus 3h over h. And the h's cancel. And so we're just left with negative 6x minus 3h. This is something from the first week of class that I feel like might be difficult for most students, and I really want you to practice it. So really get a hold of this. This is an important one for us. There's a lot of steps. I think that each step is easy enough, but it takes a little practice. So, don't go, oh, well, I don't understand it, so I'll just skip it. This is one of the core things we're learning. So definitely understand how to do it. You got this week to practice it. Okay, so that's how I got the difference quotient. Now, the next part is evaluate the table, okay? And they want me to evaluate this negative 6x minus 3h over here. What if x equals 5? And what if h equals 2? Okay, negative 6 times 5 minus 3 times 2. Let's see where I got the negative 36. Now, what if x still equals 5, but h equals 1? Negative 6 times 5 minus 3, 1. Negative 15. Whoops, I must have hit something. Negative 6 times 5 minus 3 times 1. Oh, I mistyped it. My brain's starting tired. Negative 6 times 5 minus 3 times 1. Negative 33. Five 0.01, right? Negative 6 times 5 minus 3 times 7. Right? Closer, closer. If 6 times 5 minus 3 times 0.01. No. Okay. So it looks like as h gets closer and closer to 0, this is getting closer and closer to negative 30. And that's something we're going to talk about next time, is the limit as h approaches 0. We can see we're kind of ramping this up. Any questions about that? Next one was 5. I think it was the same idea. I just want to make sure that it made sense how to do it. And I know that difference quotient can be tricky. I want to give lots of examples. So this is going to be a huge deal for us. It's going to be the definition of a limit. So that's what we're doing. All right, so f of x is negative 4x plus 5. We want to find that difference quotient there. So that means that f of x plus h minus f of x over h equals minus 4x plus h plus 5 minus negative 4x plus 5 over h negative 4x minus 4h plus 5 plus 4x minus 5 over h. And what cancels? Seems like something ought to cancel. 4x cancels, 5 cancels, and I'm left with negative 4h over h. And the h's cancel. Left with negative 4. Well, what we showed, we just formally proved that the slope of this line is negative 4. That's what we'll tie in next week, is that we just proved that the slope of this line is negative 4, which we already knew before, but now we're going to develop the tools. What if it's not a straight line? So there it is. We have negative 4. Now, what if h equals 2? What if h equals 1? What if h equals 0.1? What if h equals 0.01? Well, it's always a constant negative 4 there, right? That's always just negative 4. So it's always negative 4. It's just the slope. It's just the slope of the line. And so next week, we're going to look at how do you find the slope of a curvy line at a particular point. We'll look at that. So that's what we're hearing for. That's the idea. Okay, the next one I wanted to look at, that was 45. Okay, I have something to say about the next one. 46. I don't remember what it was. Okay, it's similar. They give us a function. F of x equals 5x squared minus 3x. And we have to find the difference quotient. Okay, they give us that formula right here. All right, so how do you find that? F of x plus h minus f of x over h. 5x plus h squared minus 3x plus h minus the function itself, 5 x squared minus 3x over h. Okay, let's see what happens. 5 times x squared plus 2hx plus h squared minus 3x minus 3h minus 5x squared plus 3x over h, 5x squared plus 10hx plus 5h squared minus 3x minus 3h minus 5x squared plus 3x. This is the step where something ought to cancel. Looks like it does. 5x squared cancels. 3x cancels. And that should do. And hx 5h squared minus 3h over h. This is the factoring out part. 10x 5h minus 3 over h. 10x 5h minus 3. Good. It's a lot of steps, but each step is not that bad. And I can't believe I haven't made a mistake yet, but even if you do this problem a million times, you'll still make mistakes. So you just gotta let that go and then just keep practicing. And I still goof up all the time. It's easy to understand what to do. It's just annoying to do it. Okay, and then now that we found the difference quotient, the next part is what if x equals 5 and what if h equals 2? And then you'll just evaluate it like you did before. I'm going to leave that part to you because I feel like out of the two parts, that was the harder one. So I feel like you should have an idea of what to do. And that was question 46. And the next one I wanted to go over was 47. Okay. One was 47. Something to do with lines. I don't remember what. This is the graph shows the number of trips taken annually on a certain state's mass transportation system. Find the average rate of change, which is slope, for the number of trips from 92 to 95, 95 to 2000, 92 to 98. Okay, so we have to do that. So let's do it. Average rate of change from these years. The first one was 92 to 95. 92 to 95. All right. So let's find the average rate of change. Remember, that is just slope. So 92 to 95, the slope is just 7.5 minus 8.6 over 95 minus 92. So it's just the slope of the line. From 95 to 2000, we're looking at the slope being 9.8 minus 7.5 over 5 years. And then from 92 to 98, the slope is 8.8, 8.6, 6 years. It's just the slope of the line. Even though this is a curvy line, we can still do average rate of change between 2 points or 2 times. So even though it's not a straight line, for instance, if we're looking at from 92 to 98, that's not quite how I wanted it. You can think of that line and find the slope of that line. Even though it dipped well below that, you go, okay, this is the average rate of change if you just look at those 2 points. That's the idea. And that would be the secant line if we're thinking about it geometrically. But we're not, because we don't do trig in this class. Okay, that was 47. The next one I wanted to talk about was so it's just 48. That was the next one I wanted to mention. Don't remember what it was. Really, it was the last part. I wanted to make sure it was okay. The average price of ticket to a baseball game can be approximated by P of X 0.03x squared plus 0.49x plus 0.947, where X is the number of years after 1991, and P of X is in dollars. So when it says P of 5, we're just evaluating at 5. Okay. So you should remember that from algebra class. So you're just plugging in 5 for X, nothing. And that would be true with P of 15, you're just plugging it in, seeing what happens. The next part's a little interesting that you can do this. The P of 15 minus P of 5 really is, you can just subtract their them being evaluated. And that has a lot of consequences that you can do that. It probably doesn't seem that interesting to you because you've been doing it all through high school and such, but that also means that you could do that with limits, believe it or not. So that means that if two functions go to this limit, that you could subtract their limits as well. So that's interesting. Okay, and then here you're finding the average rate of change. So P of 15 minus P of 5 over 15 minus 5. Well, that's just, we evaluate it at P of 15. We already did that. 23.57 minus 12.67 over 15 minus 5. 1.09. So it's the average rate of change there. Average rate of change. These are like the y values. It's like y when x equals 15. That's like y x equals 5. This is like x equals 15, x equals 5. So that's a slope. That's just a slope. And then which of the following is appropriate interpretation of the results? I would say from 1996 to 2006, the average price of the ticket increased on average by this amount. It's increasing by this amount. And that kind of came from the story problem, but I would agree that it's increasing, okay? Increasing. I wouldn't say it's hard, but I just wanted to mention that notation. Sure it's clear to do. That was problem 47. Comments on 48. Maybe a few. Oh, that is 48. 49. Didn't write anything, but I have it written down to talk about it. I don't remember what it was, so let's see what it was. Oh, this one's kind of interesting. I don't know if it's true, but it's interesting if it is true. The total number of words, M of T, that a person can memorize in T minutes is shown in the graph below. Complete parts A and B to the right. So let's go from the beginning. So find the average rate of change of M as T changes from 0 to 8, from 8 to 16, 16 to 24, 24 to 32, and 32 to 36. Average rate of change is just slope. So find the slope. And you do that just by looking at that graph. So from 0 to 8, well, that's 0, 0, and 8, 4. So you can just find the slope that way. So that just is 1/2. That's not too bad. Average rate of change from 8 to 16, very similar. 8 to 16. And so on and so on and so on. But what I wanted to really talk about, these parts. I thought this was interesting. So it says the average rate of change is M changes from 24 to 32 and 32 to 36. Let's look at that graph. So it has this horizontal asymptote. So it's pretty much just leveling off right there. So you see it's just leveling off at 20, 20, and 20. So it seems like that was the maximum amount that they could memorize at this given time. So it's leveling off. I thought that was kind of interesting that it was doing that. I don't know if it's true, but the function's at least interesting. So that's where the 0 and 0 is coming from, because it's not changing. Okay. Explain the behavior of the average rate of change after 24 minutes, and that's what I was trying to say. The graph becomes horizontal, and therefore the slope is 0. It's like it's not changing. So, particularly difficult, but I thought we should talk about it. That was 49. Should probably pick my problems more carefully now. 50. An object dropped from rest to the top of a tall building on planet X falls with a distance of 11 t squared feet. Find the average rate of change with respect to t equaling 6 seconds and t equaling 9 seconds. Okay, so this is just, it says average rate of change. It just means find the slope. Just find the slope. Okay, the slope would be 11, 9 squared minus 11, 6 squared over 9 minus 6. That's what I did. Okay, so nothing too taxing. It's just finding the slope. That's how I did it. It kind of sounds hard because we're talking about gravity, but it's not too bad. What's the next one? D1. Talked about 50. What was it about this one I wanted to bring up? I don't remember. It says the graph gives the distance d in miles you are from home as a function of t in hours. We have d equals f of t. Find f of 0. Okay, that's where x equals 0. And it looks like that would just be the y-intercept. Looks like that's just 45 miles. Use the line segment to represent the average rate of change over the interval of 3 to 6. That's just going to be find the slope. So find the slope at 6 and 3. And what does it equal at 6? Looks like it equals 15. And what does it equal at 3? Looks like it equals 3. So that's where I found that slope. And what's the other part you have to do? So that's where I got the 4 miles per hour. And then that is your average speed you're traveling from home, and you have to check that from the story problem. So you'll have to read over that yourself, but the story problem says average from home. So I'll save a picture of that. Just want to bring that to your attention. And that was 51. And let's look over 52 and just make sure. Average rate of change again. So the table gives a profit P of the fast food chain. Yeah, you're just finding the slope. You're just gonna find the slope. Okay, so that's up to you. Okay, so what's due? What is due for the class? We have 4 things to do this week. So if I go to calendar, you'll see it. If you go to the front page, you'll see it. Hopefully. You don't care about my finite class. You have homework 1A, quiz 1A, 1B, quiz 1B. Quiz is timed, but you have more than one attempt. Okay. So, and it really is just the homework. The quizzes are really just the homework. So if you complete all the homework and you take good notes for yourself, I don't think you're gonna have any trouble with the quizzes. And that's the same with my other class I teach. The quizzes are really just more of the homework. So if you're doing the homework, I think if you're having trouble, reach out. And like I say, you can email me. I don't really have office hours anymore. But you can just email me. Sure, it's on the solo somewhere. There's my email address, and yeah, just send me a message. You can also send me a message through the My Math Lab. If it's a homework question, I guess I would prefer that because it'll send me a link and I can look at it. Okay. Well, until next time, I'll see you then, and let me know if you have any questions. Yeah, I'll post this lecture later today, okay?
Thank you.